look at the complexity of arc consistency. So for now, we're only going to consider binary constraints. We're going to assume that each variable has a domain size of D, and there are E arcs. So I want the complexity now in terms of D and E. How long does it take? So if we think of checking an arc, we'll think about if we check an arc, so what do we need to do? Well, for each domain of one of the variables, you have to check the domains of the others. Right, so it takes order of D squared. So we have X and a constraint between X and Y, and so for each value of X, we have to check each value of Y. So that's why it's order of D squared. Now, if you think about how much time each constraint needs to be checked, well, it happens only needs to be checked for this constraint has to be rechecked whenever the domain of Y, a value is reduced. And it can only be reduced D times, because that's how big the domain size is. Right, so it has to be checked at most D times. Therefore, the algorithm takes at most the order of ED cubed. So E is the number of arcs, D is the number of, is the domain size, but it's the domain size cubed. That's the complexity of this. So it turns out that solving a CSP is an NP-complete problem, where N is the number of variables. So that's NP-complete in the number of variables. So NP-complete means given a solution, it can be checked in polynomial time. But then it can be made arc consistent in polynomial time. Well, how could that be the case but when we know that we can't solve NP hard problems, NP complete problems in polynomial time? We don't know it theoretically, but practically we know we can't solve NP complete problems in polynomial time. NP hard problems in polynomial time. Okay, so, and the answer has to be that making the network arc consistent doesn't actually solve the problem. We still need to do some search. Okay, so what we're going to do is we're going to find arc consistency, find solutions with arc consistency and domain splitting. So to solve a CSP, we're going to simplify with arc consistency. So if one of the domains is empty, we're going to return no solutions. If all domains have size 1, we're going to return the solution found. Otherwise, we're going to split a domain and recursively solve each half. So let's try and write that in pseudocode, just exactly what I said there. We're going to call it solve one. We're going to find one solution to this. It's got CSP and a set of all the reduced domains. We can simplify the CSP with arc consistency, the first thing. If one domain is empty, we're going to return false, meaning there's no solution. If all the domains have one element, then we're going to return that assignment. We're going to, for each element, we're going to assign, each variable has a domain with one element, so we're going to assign that element to that variable. Otherwise, we're going to set if that's not true, that at least one of the variables has a domain that's bigger than one, so we're going to select one of them. We're going to partition this into two elements, D1 and D2, and then we're going to solve one CSP. These are now simpler CSPs because the domain size of X is reduced. So these are both simpler than before. We solve one of them. If that returns a solution, return it. But if that returns false, we're going to return the other one. So that's how you can find one solution without consistency in domain solving. This is solve one. That's given in the code. To solve all of them, well, it's almost the same algorithm. Let's go for here's finding all of them. Here's solve one. So we're just going to replace parts of it. So if one domain is empty, what do we do? Well, if one domain is empty, the set of all solutions is the empty set. If all domain has one element, we're going to turn the set that contains the solution of that element for each variable. Otherwise, we're just going to do what we did before, is we're going to solve two problems, but now instead of just doing all of them, because we only want one answer, we're going to do the union of them. So this returns the set of all values with the domain X as D1. This returns the domain X as D2, and we get the union of those two things. So now we can also view it in terms of our previous search algorithms. So we can also view it in terms of our previous search algorithms, adding it into the search domain we did before. So remember, when we defined a search algorithm, we need to define the nodes, the neighbors, the goal, and the start node. Okay, so that's what we're going to do here. So the nodes here are this constraint satisfaction problem with arc-consistent domains. So for any node, the neighbor of a node is basically says if all the domains are non-empty, we're going to select the variable, partition it into these and the neighbors are now going to be the reduced domains. So now I can search. This is the neighbor. It has two neighbors. So we're going to search here. We could do it into each of the values, but here I'm just going to split it into two. The goal is to find something where all domains have size 1. That's what we're trying to find. And the start node is just going to make the CSP arc consistent. So this is how we're going to convert the problem of arc consistency with search. And we'll find that the search algorithm, if we do this, is much smaller than the search algorithm it is before, because lots of pruning helps us.